And whatever discussion we are going to do here, one thing we are going to assume that the potential across the surface is constant and zero drain to source voltage. I am going to apply zero VDS equal to zero, and the potential is going to be same across the surface. With this assumption, the induced charge is proportional to the gate voltage. So how much amount of charges are induced is proportional to the amount of voltage I apply at the gate. It is very clear. If I apply more positive voltage, I get more negative charges. If I apply more negative voltage, I get more positive charges. So what voltage I am going to apply, that is going to depend on, that is going to produce an equal and opposite amount of charges on the other side of the thing. And I'm going to assume the charge density is going to be constant. Across the channel, the number of charge carriers per unit volume is going to be constant. So now slowly, I have not applied any VDS. I have assumed VDS equals 0. I'm just varying VGS. Now what I'm going to do, if I'm slowly applying a positive drain voltage V, if I slowly increase the drain voltage V, then the channel must increase from 0 to source end to V at the drain end. So if I apply a drain voltage V, the potential across the channel is also going to vary. So what happens at one end, the potential will be 0. At one end, the potential will be equal to V. You see here, there is a potential difference happening as you move from source towards your drain, because I am applying a positive voltage at the drain. See, when you say VDS, it is drain is positive and source is negative. This is the voltage what you give VDS. And VGS, if you say gate is positive and source is negative. So this is the voltage what you give for VGS. So I maintain gate voltage VGS, and now I slowly give a positive voltage VDS to my device. I can see at the channel charge density is varying from the maximum at the source. You know, when I'm giving positive voltage to the drain and negative voltage to your source, I have maximum charge density at the source side, and it slowly reduces and becomes minimum at the drain side. And the potential is going to be VGS minus channel potential, that is also largest at the source side, and it becomes zero, or I can say it is not exactly zero, it is a minimal at the drain side, representing the charge. So this triangular region represents the charge density. On the source side, you have a large charge density, and it diminishes as it moves from the source towards your drain. Since there is a potential field set up across the channel, because I'm giving VDS across the channel, because of the constant potential which is available across the channel, there is a varying charge density available across the channel. So I can give the charge density of this form. Charge density is given by Cox VGS minus V of Y minus VT. So Cox is the oxide capacitance of the oxide layer. Because of gate voltage only, these charges are getting induced, right? So that will come. You know, Q is equal to C into V. The basic formula for charge, capacitance, and voltage, Q is equal to C into V. And here, negative charge is induced, so we take minus COX and VGS minus V of Y. See, this is a varying voltage, right? So that's why I'm taking it is a function of Y. VGS minus V of Y minus VT. The VT is going to be the threshold function. Only after you apply the threshold voltage, the other side is completely devoid of the positive charges. The effective voltage is VGS minus VT minus V of Y. This V of Y is going to be a varying voltage across the channel. The channel voltage at potential at position Y. As you move along this direction Y, the channel potential is going to vary, and the variation is given by V of Y.